So good afternoon, everybody. I'm Gorka Irazoqui, as you can see it from the author list. And I'm presenting our paper, Wait a Minute, a Fast Cross-VM Attack on AES, which is a joint work with Mehmet and our two advisors, Thomas and Berk. So this is the outline that we're going to follow. First of all, we're going to talk about the motivation for us to start such a project. And then we're going to talk about the background we need to understand the attack we performed. Then we actually going to explain the attack we did on AES, and then we're going to discuss some countermeasures and give some conclusions. So let's go with the motivation. The motivation for us is pretty clear. We have a widely used system, which is the cloud system, right? And we can see it from the graph I'm putting here, in which we see that in 2005, the physical machines were much more used than virtual machines. In 2009, we have a tipping point in which the usage of both of them was almost even. And then in 2013, we see that the usage of virtual machines increased a lot. So as researchers, what we ask ourselves is if this cloud system is well isolated, if cloud providers provide isolation techniques so that one virtual machine cannot extract data from another virtual machine. And what we are interested in is if there is any hardware leakage. So we know, and we'll explain it later, that in the cloud, two users are using the same shared resources. And we want to know if, coming by that fact, one attacker can extract information from the hardware that another virtual machine has been using. So these questions were not the only ones that motivated us to start the project, but also the previous work that has been done in this area, as for example, Hey You Get Off My Cloud, which is a paper written by Ristenparr et al. And what they did here is they collocated the attacker's virtual machine with the victim's virtual machine so that they now are using the same shared resources. And this is important also because they did it in a public cloud provider such as Amazon, because now that we have virtual machine, well, victim's virtual machine and attacker's virtual machine using the same shared resources, we can apply known side channel techniques to the cloud. And that's what actually Sang et al. Did in the next paper we present, which is Home Alone. In here, they used a cache side channel technique to detect whether they were alone or not using the hardware. But they used the same cache side channel technique to extract an LGAML encryption key in the paper Cross-VM side channels, and they're used to extract private keys. They did this across the same virtual machines. So now that we have the motivation, let's talk about the background. The first thing we need to know is how the cloud environment works, right? And here I'm gonna give some main characteristics. The first one I already mentioned, I guess. So resources from a physical host are served to more than one client. This means that more than one client are going to be using either an infrastructure server or a storage server. So they are going to be sharing the resources. Also, we have to have some hidden details of infrastructure, because since we're using the hardware with some other people, having access to the full hardware would mean that we could be compromising other people's data. Also, these services are always on. This means that if we have, let's say, if we want to run a 10-hour computation, we'd rather do it in the cloud than consuming our own laptop's resources, for example. So we can move it to the cloud, and after 10 hours, we can go to the cloud and see what the result was for our computation. Also, of course, this is not free, as pretty much everything in this life. So companies usually have a fixed price depending on the machine that we're using. So the more powerful the machine we're using, the more expensive it is. And also, these servers are accessed remotely. This means that we can be here in Sweden while we're accessing a hardware or using a hardware that is in California, for example. All right, so resources in the cloud are provided for more than one user. How is this achieved? Well, thanks to virtualization technique, which has three main tasks. The first one is to provide virtual machines to the users so that users can feel that they're using their desired OS in their own physical machine, for example. Also, we have to have some abstraction level with the physical machine, again, because as we see in the picture, three guests are using the same hardware, and we have to, well, cloud providers have to implement isolation techniques and sandboxing techniques to not allow this virtual machine get data from this virtual machine, for example. So we have a hypervisor as well that controls accesses to the hardware of one of the virtual machines. And examples of these hypervisors, as you might heard are XM, VMware, and well, we have more. We have KVM, we have Hyper-V as well. And for me, those are the 4 most known ones. So examples of infrastructure cloud providers, which is what we're going to focus on. For example, we have Amazon, we have Rackspace, we have Google, and Windows, for example. So as we see, big companies are starting to offer these services because they're detecting that a lot of users are using it. So fine, we want to see if there is any leakage in the cloud. How are we going to do that? Well, we're going to try to apply side channel techniques. And the first thing that we need for that is a good cover channel in the cloud for that. And this actually is going to depend on the assumption we're going to make as attackers. Let's say that, well, the first assumption is going to be that the attacker and the victim are located in the same host. But we have to be more specific here, because they could be located in the same core. In this case, if they are located in the same core, an attacker can use any resource that is private per core. And for example, these examples are branch predictors, level 1 cache, TLBs, and so on. But this is a strong assumption because, we have machines now that have 20 cores, and being located in the same core might not be really pretty easy. So what if we go farther away? What if we want to be co-located but in different cores? Well, in this case, the attacker has to look for something that is some resource that is shared across cores, right? Luckily for us, we have in most modern processors we have a shared level of cache, which we can use as our cover channel. And the scenario is going to be, there's going to be a victim who's going to make accesses to that shared level of cache, and an adversary is going to be monitoring those accesses. So, sorry. So in order to detect those accesses, we're going to use a flash and reload, the flash and reload side channel technique, which is a low noise cache attack. We're going to explain later on why we call it low noise. And it's based on memory leakage coming from the duplication processes that are being implemented in OSs and VMs nowadays. And basically what they do is when 2 processes, let's say, are using the same shared library, instead of holding 2 copies in the physical memory, they only hold 1 copy, so that the 2 processes are accessing the same physical memory. This means that no redundant copies are stored in the physical memory. So we have an example here in which we have 3 virtual machines. Let's say, for example, virtual machine number 1 and virtual machine number 3. We see they're using NuTLS as a shared library, and instead of holding 2 copies in the rack server here, we hold only 1 copy, or they hold only 1 copy, so that both of them are using the same physical memory. So where is this implemented? This is implemented, first of all, in kernel same-page merging. Where does it appear? It appears in Linux, and it appears also in KVM, which is a Linux-based VMM. So they basically take the Linux OS and convert it into a VMM so that it can offer virtual machines. And it first appeared in kernel 2.6.32, and the basic operation is that for those pages that are declared as shareable, what they do is hash operations on those pages, and whenever they see that 2 hash operations have the same output, they merge those pages. So, but Linux is not the only one implementing this. We have a VMware as well, using what they call transparent page sharing, but the mechanism is pretty much the same. So doing hash operations at the memory page level and then merging those pages. So what are the steps for a flash and reload technique? Well, the first thing that we have to say is that we're going to work with memory lanes, maybe 1 or more. Let's say we're working with 1. So since we have shared libraries and we have duplication processes going on, victim and attacker are going to access the same memory line, the physical memory. So the first thing we do is flash the desired memory line, for example. So flashing means that we kick out that memory from any cache level of all the cache hierarchy in the physical host. So it doesn't matter if the memory line is located in the level 1 cache of another core in the physical host, this is going to be kicked out from it and go into the main memory. Then we wait until the victim runs his process, and after that we reload the memory line again, the memory line we're monitoring. And 2 things can happen. Let's see it graphically better. So we have the memory line, the red memory line that we're monitoring, and the first thing we want to do is flash it, right, to the main memory. So now it's not going to be present in the shared cache, but it's going to be in the main memory. So now the victim runs his AES encryption, for example, and 2 things can happen here. Either AES use the memory line we're monitoring, so in which case it means that it's in the shared level of cache, and this the reload time for this memory line is going to be short, whereas if it doesn't use it, it's going to be present still in the main memory, and this reload time is going to be a long reload time. And actually, you can see it pretty clearly in the next graph, right? This experiment was done in an Intel Xeon 2670, and we see clearly, well, yeah, the horizontal axis are hardware cycles, the vertical axis is the probability of accessing, well, of getting those access times. So we see that the red line refers to access times of a memory line present in the shared level of cache, and the blue line refers to access times to memory line that is in the main memory. So if we see that the difference is pretty big, right? We see that for a memory line present in the shared level of cache, we have 70 cycles more or less, and for a memory line that is present in the main memory, we have like 200 cycles. So if we put the threshold in the middle of both of them, we can get low misprediction rates, and that's why we call it a low noise cache attack. So now, since we're going to attack AES, let's have a quick AES review. AES is a symmetric block cipher, which basically takes 16 bytes of plain text and converts them into 16 bytes of ciphertext, and the key can get a size of 16, 24, or 32. And what is going to change in the AES execution if we change the key size? Well, the number of rounds implemented are going to be higher. So we can see the next slide, in which we have 4 main stages here, which are sub-bytes, shift rows, mix-arms, and add-run key, and that are repeated over, well, 9, 11, or 13 times, depending on the key size. And then we have a last round operation here, which actually doesn't implement the mixed columns. So this is going to be a fact for the attack that we're going to implement afterwards. But what typically cryptographic library designers, what they do is they merge these 3 stages into 2 stages, which are the T-table lookup operation and XOR operation. And actually, this is where the leakage is going to come from. So a T-table lookup operation is basically, we have a T-table, and we give an input to that T-table, and T-table gives us the corresponding output. So let's say that we insert input 1, 1. Well, the T-table has to go to the memory to see what's the corresponding output to the table 1, 1. And since we're accessing output number 1, 1, this is going to be present in the cache since the CPU accessed it. So, and why would we want to know the T-table accesses? Well, because the last run operation in AES looks something like this. And we can see here that basically if we get the ciphertext and we know the T-table value that has been accessed, by a simple XOR we can actually know the key. And here I only put 4 bytes, but this should be 16 bytes. So now let's see how can we merge all this to perform an attack. So again, recall that we have a small reload time if line is in the cache, and we have a long reload time if line is in the memory. So we're going to apply this to AES, detecting the T-table values again in the last round. And let's put an example here. We have the equation. Let's get one byte only. We have the picture here. Again, if we know this and we know the C as well, we can know the key used by a simple XOR. So let's assume that we monitor one memory line. And let's say that the memory line holds only 4 T-table values. So since the key is fixed and constant here, these 4 T-table values are going to be mapped into 4 different ciphertexts whenever these 4 guys are accessed. But this is a memory line, so it's loaded like that in the cache. So we cannot know which ciphertext is related to which one of these T-table values. So what we do, we're close to get the key now. But the only thing left is to try all possible keys that each ciphertext could have gotten. For example, let's say that we take the ciphertext, we XOR it with T0, T1, T2, and T3. We do the same with C1, XOR it with all the table values, and so on. So we're going to have an output like this, in which we're going to see, we're going to have 4 different sets of 4 values, and we're going to see random values all around, but one value that's going to be present in the 4 sets. So that's going to be the corrective for us. So this attack can be translated into the cloud or can be implemented into the cloud as long as the the server that the cloud system is using has a shared level of cache, because that's going to be our covert channel again. As long as the attacker and the victim are physically collocated, so therefore using the same hardware. And as long as the VMM implements memory duplication processes, which is where the leakage comes from. So if all this is accomplished, we are going to test 3 scenarios. The first one is the one in which we have a spy process in a native OS. So we have a scenario like this, in which we have a physical computer. We have a single OS. We're implementing 2 processes, or we're running 2 processes. One AES and the other one is going to be flash and reload, detecting the access that AES is doing. And here we don't have virtualization. So the second scenario is going to be that one in which we're going to have a spy process in a virtual machine. So we move to the cloud now. We have a virtual machine in the cloud, and inside the virtual machine, we're going to run 2 processes. One is going to be AES, and the other one is going to be flash and reload. Again, detecting the access that AES is making. And the third and most challenging scenario is going to be that one in which we have 2 virtual machines, so a cross-VM attack. One of them is implementing AES, and the other one is trying to guess what the other virtual machine is accessing. Again, using the same physical host. So our test setup is going to be, we're going to use VMware ESXi 5.5 as our VMM. We're going to use Ubuntu 12.04 as our guest OSs. We're going to use an Intel i5 3320, which looks something like this, in which we see the 4 different cores here, and we clearly see the covert channel, right? So we're going to put attacker and victim in different cores, and we're going to use the shared level 3 cache as a covert channel. We're going to use the same implementation of AES of OpenSSL 101F, and we're going to have transparent page sharing enabled. So the results are presented here, in which we have, the vertical axis refers to the number of correct key bytes guessed, and the horizontal axis refers to the number of encryptions needed to get the key. So we see also 3 lines. The blue one refers to the scenario in which we have a single OS. The green one refers to the scenario in which we have a single VM, and then the red line refers to the scenario in which we have a cross-VM attack. So the first thing that we have to see here in the graph is that we get the whole key, the 16 bytes of the key for the 3 cases. But we need more encryptions in some, well, yeah, this was kind of a surprise, but okay. So we need a different number of encryptions for each one of them. For the first one, we need 100,000 encryptions. For the second one, we need 200,000 encryptions. And for the cross-VM attack, we need 400,000 encryptions. But surprisingly, even though they seem a lot of encryptions, all these measurements were taken under a minute. So the first scenario took like 12 seconds. The second scenario took like 26. And the most challenging one, the cross-VM attack, took like 55 seconds. So this is important. We are getting an AES key that we cannot get via brute force attacks with the computational resources that we have nowadays. So we're getting it thanks to side channel attacks in less than a minute. So this is how powerful side channel attacks can be. Also, we can compare our side channel attack to other side channel attacks that have been applied to AES. And under the same settings, we see that we improve over many of the side channel attacks that exist nowadays, except for this one. But this one is this one is assuming that they're blocking the AES execution, so it's a less realistic scenario than ours. And in the cloud, only a Bernstein attack has been applied in the cloud, and they need 2 to the 30 encryptions, and actually they didn't recover the whole key, only key bits. And we get the whole key with 400,000 encryptions. So we see that we have an improvement over most of the attacks that have been applied to AES. So we have a leakage here, and how can we evict it? How can we avoid it? Well, yeah, we can have software countermeasures here. And in the case of AES, we can use cache prefetching. Cache prefetching simply means that if we are going to access for one table value, for example, instead of accessing one of them, we put all of them in the cache. So now the victim is going to come, and he's going to say, I want to distinguish which one has been accessed or not. And he's going to find out that all the table values are in the cache. So he cannot distinguish whether one t-table value was accessed or not. Then we have a cache flashing process. We can have a cache flashing process as well, in which we do the same thing but in the opposite direction. So instead of putting all of them in the cache, we put all of them in memory. So now the attacker, again, he's going to try to check whether one t-table value has been accessed or not, and he's going to find out that all of them are in the main memory, and therefore he cannot distinguish here. We can have hardware countermeasures as well, in which, let's say that we have a shared level 3 cache, and instead of using the whole cache for all the tenants, we split it and we divide it into pieces so that each tenant uses one portion of the cache only. So each tenant is allowed to only use one portion of the cache. So now we cannot have interference here between across tenants, and no cache side channel attacks are possible in this scenario. Well, there is another solution also. Let's say that we are doing the duplication process again, and let's say that we apply a private offset when the memory loads the data into the cache. We apply the private offset per VM or per process. So this means that when VM1 accesses this data, and when VM2 accesses the same data, since the offset that they apply to load it into the cache, it's different and private. So they're not going to be, well, the same data is not going to be mapped into the same data in the cache. So when VM2, for example, let's say that VM2 is the attacker, tries to guess whether the data is in the cache or not, he's going to find out that he has a private data, and yeah, he cannot perform cache side channel attacks. So in conclusion, we have a hardware leakage existing in cloud environments, and yeah, so cloud providers should avoid that using isolation techniques, for example, more precise isolation techniques in the hardware. Also, we see that flash and reload improves over many other side channel attacks on AES. So, depending on of course, on the assumptions that we make as attackers, but we saw that we improved over most of them. And also, we see that the duplication is a potential risk, even though it's translated in more memory savings. So we see that it's a potential risk, and it's a covert channel that one attacker can use to infer an AES key, for example. And actually, VMware contacted us and reproduced our attacks, and they released a document in which they say what's the configuration that a user has to put in VMware to avoid this kind of leakage. So I encourage you to read the document if you have any doubt. So that was all. Thank you, and I'll try to answer all the questions that you have.
Okay, let me kick off asking a question about the various choices of countermeasure.
Yeah.
There seem to be many approaches, and perhaps also more than just the ones you listed to tackling this. So how should one go about evaluating what is the best way? I mean, it's all about performance, I guess.
Yeah, well, in case of software countermeasures, I guess it's depending on how much speed you lose in the AES execution, right? So some countermeasures involve more latency than another ones. So I guess in the case of software countermeasures, I would actually go for how much time do I lose implementing these countermeasures on AES. And in case of hardware countermeasures, I think that the one of splitting the cache, for example, can be more difficult to implement. But the one of adding a random offset is just a simple XOR. So I think that's much more simple. You don't lose many space on the physical hardware by putting an XOR operation. So I guess this depends on it's a trade-off, right?
But the countermeasures you describe are very generic.
Yeah.
Couldn't one be much more specific? I mean, it's a very specific bit of information that's being shared, that's being shared across different machines.
Yes.
The tables. Could you add salt to the tables, for example, a machine-specific bit of?
But the problem is that this kind of a flash and reload attack, for example, can be applied on not only on AES, but it can be applied also on RSA, any other cipher that uses shared memory.
So what you're saying is we really need a generic solution because it's a problem that's going to pop up over and over again.
Yeah. But yeah, in the case of AES, you can mask the t-tables, for example, so that with different masks and yeah, the victim wouldn't have any problem.
Any questions? Okay, well, we'll leave it as a question then. Very good.
So this was Intel specific. Would you say that Spark processor, for example, have similar issues?
Yeah, but in the case of Intel, for example, I didn't mention it, but yeah, in the case of Intel released, well, in most modern processor, Intel released AES, what we call AES new instructions, that they don't use memory. So this cache sidechain attacks on AES at least wouldn't be possible in Intel, but any other hardware provider that doesn't have this kind of specific AES instructions, yeah, this attack can be applied on them as well. Yeah.
Would changing the type of AES you use make a difference? Like using longer?
Yes, definitely. For example, we said that they merge the 4 stages into 2 stages, which are T-table and an XOR. Well, there are some implementations for embedded processors, for example, that use smaller tables. Well, if they use smaller tables, this means that they are more likely to be accessed. All of the T-table values are more likely to be accessed during the execution. So this means that all the T-table values are more likely to be in the cache after the AES execution, and the attacker now cannot decide whether one of them was accessed or not again. So definitely yes.
Okay, let's thank our speaker again. Thank you.